We're now going to look at how energy ties in and relates to work, power, and machines. And this is chapter 6 out of your textbook, where the energy, kinetic, and potential is chapter 5 out of your book. Now, the first question to ask is, what is work? To many people, work simply means something that they do, that they have to do in order to get, of course, money. And the word work also means exerting, sometimes exerting a force with your muscles. And so a lot of people say, oh, that was a lot of work. They had to carry something up some stairs. And someone might even say that they've done work when they push onto a wall as hard as they can, but yet the wall doesn't move because they feel like, well, they're still exerting their muscles, they're still expending energy. But science has a different definition. Work is used in a different way and a very specific definition. Now, work is related to forces. We know that a force is a push or a pull, and in order for work to be done, a force must make something move. It has to move or else work hasn't been done. And so work is energy. It's the transfer of energy that occurs when a force makes an object move. So in the picture, you can push this car as much as you can, but if it doesn't move, in the science world, you technically have not done any work. Now, there are two conditions that must be satisfied in order for work to be done, and we kind of mentioned the first one already. The applied force must make the object move. But the second catch is the movement must be in the same direction as the applied force. Now let's look at an example showing that second criterion. Let's say when you're at your locker and you put a whole bunch of books on the ground and you pick them up to head to your next class. Now, the force, the direction is up, so you can draw an upward arrow there. And the direction that the object is moving is also up. And because the force and the distance, or the direction, are the same, or they're in the same direction, your arms have done work. And notice it's in yellow on the books. And so you also have to kind of talk about which object you're doing work on. So you have done work on the books because they're moving in the same direction as the force that is applied. Now, as you take those books and you walk to class, carrying books while walking is not, in the science world, doing work on the books. Now, your muscles might be moving something, but on the books they're not doing work because the force and direction are opposite, or they're not in the same direction. And the little cartoon on the bottom, if you're a waitress, technically you're not doing work on the food because the force on the tray and the direction of the tray are different. And so just a little humor there. Moving on. And so let's relate work and energy. When work is done, a transfer of energy always occurs. Said and done. This is easy to understand because when you think about how you feel after carrying a heavy box up a flight of stairs, you can feel that energy has been transferred. You're transferring energy from your moving muscles to the box, and you're transferring that energy to potential energy because you're increasing its height on the stairs. Now, when you look at this relationship with work and energy, if a transfer of energy always occurs when work is done, that means work is energy or equals energy. So you can, I know it's a little cut off there, you can put that in there, work equals energy. And so when you do calculations with work, that means if it's energy, that you need to be using the energy unit of a joule. Okay, and so with the definition, the amount of work done depends on the amount of force exerted and the distance over which the force is applied. And so there's your equation. Work equals the amount of force in newtons times the distance in meters that it is exerted upon. And so you can calculate that, and we'll do a couple of examples as well, of course, in class. And so when you look at when is work done, let's say you push a book and it slides across the table for a distance of 1 meter before it comes to a stop. Even though the book moved 1 meter, you do work on the book only while your hand is in contact with it. So if you just touched it and it slid, the work that was applied is only during the time when you are touching the book or applying the force. And so that's one little catch to these problems. You have to make sure that the force is being exerted across the entire distance. Now, if we look here and we do some examples, how much work does an elephant do while pushing a circus wagon 20 meters with a pulling force of 200 newtons? So when you plug this into the equation, we know that work, capital W, is equal to your force, which would be the 200 newtons. Now, one of the reasons why this is so bad is because I am left-handed, but yet I do use my right hand for the mouse, and so it doesn't look very good, and the left hand doesn't work any better with the mouse either. So anyway, so here's your force, 200 newtons. So use your units to know which one, where things go. Your distance here would be at 20 meters. So we plug all that in, multiply, work equals 4,000. Now look at the units here. It's always important to understand what the units mean. When you put together Newton and meter, well, you get a Newton meter. Well, we know that work is energy, so the units for work should be joules, which they are, because a joule, and go ahead and add this into your notes, is equal to a Newton meter. And remember, a Newton is kilograms times meters per second squared, so you can plug that in as well, and you get the same thing. So a joule is a pretty complicated unit. Now let's look at the next example. Tommy does 15 joules of work to push the pencil over 1.5 meters. Now a pencil is very small, so obviously it's not a lot of work done. It's a pretty low joules because the joule is very small. So what we want to know is how much force does Tommy have to push the pencil with in order to exert this much energy. So when you plug it in, if the joules means work, so you've got 15 joules, that's your work, is equal to your force, that's our unknown, so you leave it alone. Force times your distance of 1.5 meters. So we divide both sides by 1.5, and we get force is equal to, hopefully we can do that in our head, 10. Now remember, we're dividing a joule by meter. Joule is a Newton meter, so if you divide by meters, the meters cancel out. We should be left with 10 newtons of force that must be exerted. Again, makes sense because pencils are very small and you don't need a lot of force in order to move it. Now that we know how much, or how to calculate how much work is being done, let's look at how that relates to power. Now let's say that you have to move this weekend, which is an awful thing, but anyway, let's say you have to move some boxes into the truck. Okay, and so not an exciting job, but to make the job more fun, let's say you make a game of it, racing to see who can push a box up the ramp faster. Now, you know that if you are applying a force to the box and over a certain distance, that work is being done. But now, when you're looking at who can do it faster, you're adding in a factor of time. And so you're looking at more of a rate, which is what power is. Power is the amount of work done in 1 second. Now, of course, 1 second is a short period of time, and so again, the numbers are going to be rather small. But because it's over time, it is a rate, the rate at which work is done. Now, to calculate that, we know that with rates, we always divide by time. And so power, and this is where our capital P comes in. Remember when we talked about momentum, we can't use a capital P for momentum because it's already used for power. So capital P is equal to capital W, which is work, divided by time. So you've got joules divided by time, which turns out to be an all familiar unit, the watt. And so the international system for power is the watt, and this is used even in the US. 1 watt equals 1 joule of work done in 1 second. So those light bulbs you can kind of relate to as far as how much energy is being exerted in 1 second. Now because watts and joules and seconds are so small, we often use the kilowatts because a lot of times your answers tend to be rather large. Now let's look at the relationship again, but with power and energy. We know that power is the rate at which work is done, and we talked about a few minutes ago that work is energy. So therefore, power is also the rate at which energy is transferred. And so we look at that also like with the light bulbs, because we're really using energy versus work with a force over a distance. And so this is the same equation, you're just switching out one letter. Because work is energy, you can use a capital W or you can use an E depending on the situation or depending on the problem. Now, where does this come from? We all know the familiar horsepower rating, maybe for cars. And so just a brief history with this. The horsepower is equal to, it was how much power or work a horse could do in a certain amount of time. And so it goes back to the fact that they figured out that a horse could lift or move 33,000 pounds 1 foot, a distance of 1 foot per minute. And so that's kind of the background of where the horsepower came from. And so, but they still do use that kind of conversion and relationship with cars, but not too much for work itself and power itself. Now let's look at an example of power to finish up the video that kind of ties all of it together. And so we know that the equation for power is work divided by time. Now the question is, a woman runs a kilometer using a force of 210 newtons and uses a power output of 500 watts. How long in minutes does it take this woman to complete 1 kilometer? Now notice the question is how long in minutes. So when we write the equation, we know that we're going to be solving for time. That is our unknown right there. Now they use 500 watts of power. And remember, you got to remember the units. So 500 watts, I'm having a hard time writing here, is equal to work divided by time. Now we know that time is our unknown, so we'll put that there. The problem is work. Work, the unit for work is it's energy in joules. Well, they don't give that to you. So you have to utilize the information in the problem in order to figure out work. All right, and from earlier in the video, we know that work equals how much force they exert over a specific distance. And I'm about to put meters, but that should be distance. So to figure out the work that is done, we take the force exerted, which is 210 newtons, 210 newtons, and you multiply that across the distance that they are applying that. Well, they have to exert that over the entire distance of a kilometer. Now remember, the units for distance have to be in meters, and so we would change that over then to 1,000 meters. So when you multiply these two together, you end up getting 210,000 Newton meters or joules. And so you plug that in over here. So you get 210,000. This is really looking awful, but as long as you're listening, you should be okay. Now to solve this, you multiply both sides by t. We've done this all year long so far, and then you'll divide both sides then by 500. And when you do that, you should end up getting a power output, time, I'm looking up here. When we solve for t, because you're going to divide both sides by 500 to get t by itself, t is going to give you 420. Now you ask yourself, what is the unit? And we know that power is the amount of work done per second. So this gives us 420 seconds. The question asks you, though, how long in minutes? So what we do is we divide by 60, which will then tell you that it'll take this person 7 minutes in order, and I should put minutes, M-I-N,